In this work, we study the problem of robust visual navigation where agents learn to encode the impact of their actions to overcome motion drifts. When navigating within a novel scene, agents may encounter many unexpected conditions. For example, an agent trained on carpets must calibrate itself to move robustly on bamboo floors. Take real-world indoor navigation as another example. Here the agent moves faster, more smoothly, and further on this paper floor. In contrast, it moves slower and less smoothly on a canvas floor. Worse yet, when the robot's wheel is obstructed by tape, dust, or hair, the outcomes of actions are even more severely disturbed. In this work, we call these changes in how an agent's actions influence the environment as motion drifts. Our goal is to learn a robust policy that allows the agent to adapt to unexpected drifts. To study this problem, we consider the point navigation and object navigation tasks. To train our agent's policy, we sample movement and rotation drifts at the beginning of an episode. Note that these drifts are usually larger in magnitude than standard high-frequency actuator noise. At testing, we sample drifts from novel distributions unseen in the training stage. For example, the agent may experience 0.1 movement drifts during the evaluation stage when, during training, it never saw drifts greater than 0.05. Take move actions as an example. When we move the agent by 0.2 meters, a 0.05 drift makes the agent move 0.05 meters further than expected. Conversely, a negative 0.05 drift makes the agent move a shorter distance. Similarly, for rotation actions, a rotation drift changes the degree of rotation significantly. To address these motion drifts, our first idea is to implicitly encode how actions actually behave during every episode. For example, when experiencing a drift of 15 degrees in magnitude during training, taking a 90-degree rotation action would result in the agent actually rotating by 75 or 105 degrees. Similarly, for a 60-degree rotation action, we propose not to encode the semantics meaning of actions but instead encode their actual impact. In other words, we do not want our agent to memorize that its first action results in a 90-degree rotation and that its second action results in a 60-degree rotation. We instead want the agent to encode the actual outcome of its actions on the fly. To this end, we design our agent's action embeddings so that each dimension of the embeddings represents that action's observed impact. For example, when taking action 0, the agent records an embedding of the 105-degree rotation outcome at dimension 0. Similarly, an embedding of the 45-degree rotation outcome at dimension I. When the agent faces a novel drift when taking action j, it needs only record the outcome of that action at dimension j. In this way, the agent can choose which action to execute based on the expected impact of that action, which may be informed by its experience. However, by itself, this action impact embedding idea is insufficient to produce robust agents. This is because the linear actor typically used for embodied agents will, in practice, memorize the action semantics while ignoring the action embedding. The reason for this is that we have fixed model parameters for each action. For example, the blue weights vectors here are only for the first action, and the orange weights vectors are only for the final action. In our experiments, we show that this fixed mapping results in brittle agents which memorize action semantics. To solve this issue, we propose to use a transformer model as our actor. The weight sharing in the transformer breaks the fixed mapping issue and requires the agent to choose which action to execute based solely on the action's expected impacts. Here is a standard agent policy model used frequently in embodied AI tasks. This policy includes a state encoder and a policy network. We further introduce an action impact encoder and an order invariant head, shown in purple. The action impact encoder produces the action embeddings, encoding observed action impact. The order invariant head is a transformer model. We call our model the action adaptive policy app. In our app, when the agent executes action I, the action impact encoder uses consecutive visual observations to summarize the state change and saves the result into Embedding AI. In particular, Action Impact Encoder takes as input consecutive visual observations, task goals, and the previous action with index I. The output of this encoder is then passed to a recurrent neural network whose hidden state is taken from the ith dimension of memory. The output of this recurrent network then replaces the previous action embedding at dimension I. In the policy network, we have another recurrent network to encode the agent's belief state. However, we replace the standard linear actor head with our transformer-based order invariant head. We conducted experiments in 3 environments: RoboTHOR, Habitat, and PettingZoo. Here we show the results of the point navigation task in RoboTHOR. Our method is in red. The green line is a standard baseline agent with a clip pre-trained ResNet. The blue line is a model-free meta-reinforcement learning agent which uses state prediction as its meta-objective. The orange line is a framework that aims to learn a latent code to model environment properties. At testing, it utilizes the collected states in an episode to predict the latent code. Finally, the purple line is a model-based approach, where the policy makes a decision using next state predictions. Here, the highlighted yellow region corresponds to the 15 degrees of rotation drift and 0.05 meters movement drift seen during training. As we can see, the proposed op performs consistently across all unseen rotation drifts up to even 180 degrees. For extreme movement drifts, our model still performs significantly better than competing baselines. Here are the results for the object navigation task. Again, our op performs consistently better than all the competing baseline models. In addition, in the habitat environment, our op performs consistently better than the embodied clip baseline on the point navigation across all unseen rotation drifts up to 90 degrees. In a more extreme setting, we disable all the actions related to turning left so that the agent can only accomplish a task by rotating right. Likewise, we also evaluate models where we disable all the actions related to turning right. Here we show our evaluation results on the point nav task. As we can see, our op again handily outperforms all the baselines and exhibits surprisingly consistent behavior. We show 2 qualitative results for the point navigation task here. The first results show that the agent understands that it cannot use any left turn actions, so it decides to use the actions related to the right turn to get it out of the corner. The second example here shows that even with a large 90-degree rotation drift, the agent can still move smoothly to bypass the white table to the target location. Here are 2 examples of object navigation. In the first example, the agent again demonstrates it can move smoothly to bypass the wall and find the target object, a basketball. The second example shows that the agent uses multiple slight right turns to achieve the disabled left turn. In addition, we conduct an exploratory experiment on object navigation tasks in a real-world RoboTHOR test scene. We first train our model in the ProcTHOR 10K scenes. At inference, the goal is to find an apple or chair from 2 starting locations. In the right floor plan, the apple is marked by yellow color on the table, and the chairs are marked green. We study 4 different unseen and 1 seen drift pairs. The results show that our model performs well compared to the embodied clip baseline trained with and without drifts. We show 2 qualitative results here. The first one is to find the apple on the table from location 2. The left view is the image observed by our agent. The right view is a top-down map used for visualization purposes only. Although we have 60 degrees rotation drifts and 0.1 meters movement drifts, it successfully finds the apple. Here's another example to find the chair from location 1. As we can see, although the agent collides with the bottom wall early due to the drifts, it quickly adapts itself to find the chair smoothly. Furthermore, we study a scenario closer to continuous and nonlinear control. We develop an object push task in a simple PettingZoo environment. Once again, our op as shown in purple performs very robustly compared to baselines. It solves the tasks almost 100% after 100 million training steps. Thank you for your interest in our work. Please find more details in our paper and the source code on our project page.